this table to generate different mixtures, let's say 10%, 20%, all the way to 90% CO2 and 10% and butane. And every time you are going to use these numbers to these volumes of CO2 to generate the mixture, but you need to prove one of these numbers. Okay, for example, if you decide to prove this number 0.57 in your lab report, you need to show if this is a correct number or not. Okay, so how do we do that? So to do that, the equations are already given. Okay, so here are the equations. So the volume of the CO2 required is equal to the molar volume of the CO2 times the number of moles of CO2. Okay, so that volume presented in table 4a is equal to the molar volume of CO2 times the number of mole of CO2. Number of mole of CO2 is equal to the mole percentage of CO2 times the number of moles of N-butane divided by 1 minus mole percentage of CO2. For example, if I want to prove this number 0.57, the ZCO2, the mole percentage of CO2 becomes 0.1. The number of moles of N-butane is 0.1025. So 0.1025 is number of moles of C4, and 0.1 is the CO2. So this CO2 becomes 0.1, this becomes 0.1, and this becomes 0.102. So I have this parentheses. Okay, and remember the dimension here is in mole. And so now I need to find this value, the molar volume of the CO2. So the molar volume of CO2 is defined as the molecular weight of CO2 divided by density of CO2. The molecular weight of CO2 is given. It's 44.01. Okay, and it's so it's based on the kilomole per kilogram. Okay, and then the density is also given. Okay, so density of the CO2, we need to find that. So the density is also reported in kilogram per meter cube. Okay, so this is also the density. So the molecular weight, I know that's 44.0.010. So I have that. So I need to find the density of the CO2. Okay, so to find the density of the CO2, I go to this table. This table, for different temperatures and different pressures, gives you the density of the carbon dioxide in kilogram per meter cube. Okay, so if I'm going to do this for this temperature, which is 22 degrees C or 71.6 degrees Fahrenheit, so 22 degrees C, if I come here, I have the densities at 16.9 degrees C and 26.9 degrees C. I don't have it for 22 degrees C. Okay, so I need to do the linear interpolation between these two temperatures. Okay, and for the pressure of 10 megapascal. Okay, so I don't have the density at the right temperature, which is 22 degrees C, and I don't have the temperature for the density for the right pressure, which is the pressure of my experiment. So if, let's say, your experiment is done at pressure of 2000, something around like 13 megapascal, then your density needs to be calculated at 20 degrees C and 13 megapascal, but you don't have that value. You have the density at 16.9 degrees C and 10 megapascal, 16.9 and 15 megapascal, 26.9 and 10 megapascal, and 26.9 and 15 megapascal. So you have these numbers. But what you can do the linear interpolation. You can say at 16.9 and 10 megapascal, I have a density of 878. At 26.9 and 10 megapascal, I have the density of 802. What would be the density at 22 degrees C and 10 megapascal? So you do the linear interpolation between these two numbers. So you get the density of the CO2 at 22 degrees C and 10 megapascal. You repeat the same for 15 megapascal. So you do the linear interpolation between these two numbers for 22 degrees C. So then you will have the density of the CO2 at 22 degrees C and 15 megapascal. So you will have a number here, which represents the density of CO2 at 22 degrees C and 15 megapascal, and number here, which basically gives you the density at 22 degrees C and 10 megapascal. So now you have the density at the right temperature, but not at the right pressure. Then what you say, I have it at 22 degrees C and 10 megapascal. I have it at 22 degrees C and 15 megapascal. What if I wanted to find the density at 22 degrees C and let's say 13 megapascal? So you need to do another linear interpolation between 10 megapascal and 15 megapascal to get the right density. So when you find that density will be in kilogram per meter cube, okay? So you need to bring that here. But you know, your volume of the CO2 is reported in cc's, and the number of moles of CO2 is in mole. So I need to convert this. So the kilogram goes with kilogram. The kilomole, I need to convert it to the mole, okay? So I need to, and this is wrong because we don't have the power of the 3 here, okay? So the kilomole, you need to convert that to the mole. So you just multiply with 1000. And the meter cube, you need to convert to centimeter cube, okay? So you convert the meter cube to centimeter cube and kilomole to mole. Then your molar volume would be in mole per cc, okay? So when you have the molar volume in mole per cc, you plug it here, and then you will be able to get the volume of the CO2 in cc's. Remember, since here you are going to assume that the density of the CO2 is going to linearly change with respect to temperature and linearly change with respect to pressure, and you are carrying these errors, like you're finding one value, you're doing one linear interpolation here, which basically introduces one error. You're doing another linear interpretation, so it will have another error. And then you do the third linear interpolation, which basically generates another error. So there is accumulations of errors here in your calculation. So when you find the volume of the CO2, for example, for this case, instead of getting the value exactly 0.570, you might get a value like 0.61 or 0.62, okay? So slightly different than this, but you definitely will not get a number like 0.9 or 0.1, okay? So that's okay if you get a slightly different value from what's reported in this table, but not too far, okay? So in your lab report, this is very important. This basically takes 20% of your lab report to prove one of these numbers. This goes to your analysis of the lab. And as I said before, for your lab number 1, you need to have the title page. You need to have your cover letter. Basically, the objective of this experiment is to find basically pressure composition diagram of two mixture of N-butene and CO2, and then how you did it using the PBT lab, and then basically finding the bubble point and use the gas chromatograph, and then for one point you use the smaller amount to get the dew point. The theory is basically, again, the bubble point definition, dew point definition, two-phase and behavior of the binary mixture, you know, these all the definitions that you use will go to your theory part. And then in your analysis, you need to show, you basically show your raw data, and then in your analysis, you need to prove one of these numbers presented in the table. And then in the discussion analysis, when you have generated your pressure volume, pressure composition diagram, you just compare it with what the book says and see if it makes sense or not. And then you conclude. Don't forget to put the source of errors, especially in this case, since you're doing 3 types of linear interpolation, you're introducing those errors. When you do the linear interpolation, you need to show that. You need to put that in your lab report. You need to see how you did the linear interpolation. And don't forget to put the references, okay? So in the next part, we actually start doing the lab using the PBT lab simulator, and we start collecting the data, okay?